Hello, my name is Katja Hansen. I'm an environmental engineer by training, and I've been working with Michael Braungart and the cradle-to-cradle concept for more or less 20 years. I'm currently a senior researcher at the Rotterdam School of Management, and I train a lot of companies who are interested in finding out more about cradle-to-cradle. And I'm a project manager at EPEA, Michael Braungart's organization that works on the cradle-to-cradle concept. The circular economy and cradle-to-cradle have been developing alongside each other since the early 1990s. But one distinguishing feature about cradle-to-cradle that has until recently not been covered in the circular economy are the nutrient metabolisms. These are part of a scientific concept developed by Michael Braungart and his organization EPEA. When I talk about nutrient metabolisms, I talk about biological nutrients and technical nutrients. These two nutrient metabolisms cover consumption products and service products. So when we talk about biological nutrients, we talk about materials and products that are consumed in the process of fulfilling their purpose. Examples are shampoos, detergents, but also food, for example. So it is processed. You cannot recover it. It enters the environment in diffuse pathways through the water or air, and there it should act as nutrients to create new renewable resources to make new products from. Anything that does not fit into that description actually should be described as a technical nutrient. Technical nutrients are not consumed, they're only used or borrowed, you might say. So you find it in service products. Service products are everything that surrounds us in our daily life. Cars, furniture, textiles, anything that you just use and that provides you with a service, but you don't actually use up the materials. So these are two very important metabolisms that define cradle-to-cradle. And to give you an example of one of these metabolisms, and that is the biological metabolism in more detail, I would like to tell you about a project that is the first project on cradle-to-cradle, actually developed in the early 1990s for the Earth Summit in Rio 1992. That project is called bionutrient recycling. Bionutrient recycling objective is to show that we can recycle nutrients from wastewater for safe agricultural production. The first pilot project was developed in Silva Jardim, just about 100 kilometers outside Rio de Janeiro, with the support of a chemicals company who was interested to find out what the phosphates in their detergents were actually contributing, in this case, to nutrient recovery. And later on, we had a research grant from the European Commission. So this project was developed and demonstrated then in Rio at the UNCED, the United Nations Conference on Environment and Technology, Development, United Nations Conference on Environment and Development, also called the Earth Summit, in 1992. It was one of the few, if not the only, projects at that conference that actually practically demonstrated social, economic, and environmental aspects. So we invited a whole bunch of people from Rio. We put them on buses, and we had scientists and international journalists and everyone come out to the site to actually visit this practical project. And the interesting thing was that we had the local school children from the local primary school involved in the construction of the site, and so they were there when all these international famous people arrived, and they were explaining what was happening on the facility in terms of nutrient recycling, water purification, oxygenation, pathogen elimination, and so on and so on. which was very impressive, I think, for both sides, because there you had the little children explaining fairly complicated scientific processes, and then on the other hand, the scientific community from all around the world looking at these local children, explaining that in quite a nice way. One of the visitors who also spoke to us was Professor George Lai Chan. And he complimented us on our work and said we had done a really great job, but we had made all the mistakes that he had made in earlier years. You can imagine that was quite a bit of shock, since that we had put quite a bit of scientific research into establishing that first pilot facility. And so that was our first contact with the traditional dike pond system in China. This system has been used in China for many, many, many hundreds, if not thousands of years, and it is probably one of the most productive systems in the world, both in aquaculture, that means fish production, as well as land-based crops. And the interesting thing is that these systems in southern China, and you see here an overview of a huge area that is covered, is suitable for marginal lands, i.e. those are lands that are not suitable for normal agriculture. So marginal marshy lands were used in China for this highly productive system. Now, unfortunately, what you see on this slide doesn't exist anymore, because Chinese students went to study Western technologies and intensive agriculture, and they came back home and said, we have to pave this all over, and we have to use mineral fertilizers, and we have to use intensive farming practices, when this was a system that had proven to be really, really successful. Not all of it has been paved over, but unfortunately a lot of it was lost, also of course to the exploding population and housing developments. So our group went to China and studied this system in quite a bit of detail, and we learned how they were managing the nutrient flows, and we learned also about a very important technology, and those are biogas digesters. With those tools we came back and we modified our bionutrient recycling systems and we optimized them. A bionutrient recycling system can range in size anywhere from 50 square meters to 1 to 2 hectares. What you see on this diagram, of course, is a 1 hectare site that was optimized for maximum nutrient recycling, maximum productivity, to really reuse the nutrients in the wastewater in as many multiple ways as possible. So in the upper corner, you see that there's 2 inlets to the site. One is the diluted gray water. That isn't very rich in nutrients, but it is important for the flow through the facility. But then you also have the concentrated wastewater, to which sometimes livestock waste can be added. And that passes through a biogas digester first, where we produce energy through methane, and then a very nutrient-rich effluent, which then joins the grey water stream in the first shallow algae basins, where the first purification steps are taking place. But also we grow algae, and these algae then flow into the deeper oxygenation ponds, which are important for the first purification steps. And in wastewater technology, it's called lowering the biochemical oxygen demand. That is a very important step. With these first steps taken, however, the water flows through spillways, which have a thin film water overflow, so that the water is exposed to oxygen and to UV radiation, which is important to eliminate pathogens, into the deep fish ponds. And with the algae and all the nutrients, we can actually have huge output of nutrients from these fish ponds. They're 3.5 meters deep, and I'll come back to that a little later, because that was one of the things that we learned in China. This is very unusual, because in normal aquaculture, The fish ponds are about 1.5 meters to 2 meters deep. These fish ponds do not need artificial aeration or artificial feed. Then again, through another spillway, we go into the macrophyte ponds. Those are shallower ponds that use macrophytes. Macrophytes are water-based plants, like you've seen on any of the ponds growing in your neighborhood, like duckweed, which we also call lemna. We also used water hyacinths and salvinia, depending on what the local region actually allows and what grows there. These macrophytes are very important for taking up more nutrients, also because, of course, in the fish ponds, the feces of the fish add additional nutrients to the water. So the macrophytes are converting these nutrients in the water in a next step into biomass. And that biomass is regularly harvested. And in these tropical regions like Brazil, that actually is a significant amount, and harvests can take place as often as every 2 or 3 days, because the multiplication and growth rates are very rapid in those regions. So then these plants are composted or dried or in any way returned to the soil. And then you see all the other area on that 1 or 2 hectare site is actually used for agricultural production. And again, that depends on what the local flora and fauna is like. But in Brazil, of course, we had papaya and banana and all kinds of other fruit trees. And then we were intercropping that with beans and manioc and other things. And the interesting thing in the design of these sites is also that you have a process that is called fertigation. And that is that the nutrient-rich water from these ponds infiltrates the soils around them and the dikes, so that you don't need to irrigate the areas. And, of course, you have the fertilizer in form of the nutrients that are dissolved in the water. So it is a highly productive system, and the challenge is to adapt it as much to the local requirements as needed and as possible to maximize the economic output for the farm operator, which you can also see there in the diagram, who also, as we learned in the first pilot project, can maximize their income by producing value-added things. And that is crops that are catering to special markets. For example, we had mushroom cultures of shiitake mushrooms, which of course has a much higher value than manioc on the local market. And from all the fruit, they were producing jellies and sweets, so value-added products that they were selling in the local market. So that as a result, and I can show you some of the products in the next slides, as a result, they actually had an income from these facilities, and they weren't just some wastewater treatment facilities. Just to show you an example of a much smaller facility, which is a pilot facility we built in southern China. You can see here the wastewater of a 5-story apartment building is being treated. The first 3 round circles that you see on the slide resemble the tops of the digester, and then we have a little greenhouse, and we have some aquaponics, which is plants growing on the surface of the water. So even on 50 square meters, we were able to maximize the nutrient recycling output. And in this case, we were growing a lot of flowers because that was very suitable for that region. Here you can see a few of the crops that were grown. You can see that without any artificial fertilizer or any pesticides, we were growing huge manioc roots and very large squash. In the lower left-hand side, you can see again an example for an aquaponic culture, which is really growing soil-based plants, plants that are normally grown in soil on the surface of the nutrient-rich water, which is another use of these nutrients in the water and to maximize the recycling and continuous reuse of the nutrients. And in the upper left-hand corner, you see part of the fish pond. And one very important lesson we learned on these fish ponds was that because the water doesn't flow rapidly, you might get mosquito problems and mosquito larvae actually breeding in the water. And the best natural defendant we found were local ducks. So these ducks were skimming off all the mosquito and insect larvae from these ponds, and of course they were providing another product on these sites. So that's just an example on the many ways that we can actually maximize the nutrient recovery as a beneficial thing in wastewater treatment. And then in the smaller picture in the center, you can see part of our team on the site, which when you see it from above looks more like a park and a beautiful garden area than a wastewater installation, which also has a great aesthetical value. Just coming back to the fish ponds for a second, the most important economical aspects are, of course, that we don't need to feed the fish because we provide the nutrients for the fish through the nutrients in the water. And these nutrients are, of course, converted by algae or phytoplankton, and then we have zooplankton. So we have various trophic layers in these ponds, and so various kinds of fish feed on these trophic layers. In China, they use a multicultural carp system. So they use carps, different carps that feed on these different trophic layers in the pond, as we call them. So there's a grass carp that feeds on the algae and some of the material at the upper layer. Then there is a carp that feeds on phytoplankton. Then, of course, there is a carp that feeds on zooplankton. And then there are carps called the mud carps that feed on the bottom of the pond. And then you have some omnivorous fish as well. So fish that eat pretty much everything, and they move from top to bottom and bottom to top, and that way they aerate the pond as well. And that is one of the reasons why in the Chinese culture of deep fish ponds, you don't need artificial aeration of ponds. So that's a very important aspect. The agricultural systems can be designed around the pond in a variety of configurations. In China, a lot of silkworms were being raised and grown on these dikes using the mulberry trees, which are the feed for these silkworms. That, of course, didn't work in Brazil, but like I mentioned, we had various different fruit trees and we had mushroom cultures and everything else. And the point is, it really requires very little maintenance and attention other than harvesting all the products which make you money. So that's a very good incentive to actually managing the system because you get a direct return. And then as a byproduct, we have clean water. So that is a totally different approach from conventional wastewater treatment, where we have a lot of infrastructure investment in treating an end-of-pipe problem versus actually recovering the nutrients as a beneficial thing and producing clean water as a byproduct. Here on this graph you can see that the discharge of the facility met the European wastewater discharge standards, and actually our site is the blue bars, which you can see are much lower in the standard wastewater parameters, which is the biochemical oxygen demand and the total phosphorus and total nitrogen. So what we showed in these pilot facilities in Brazil is that we could clean the water to meet the technical requirements, but more importantly, we could provide a livelihood for otherwise impoverished people in these favela areas where we built our facility. So the institute that we formed in Brazil, O Instituto Ambiental, continued with that work and they started building facilities, more and more facilities in Brazil, throughout Brazil. Then they went to Nicaragua and the Dominican Republic. And one of the recent projects was built in Haiti. The facility was completed just before the earthquake struck. And that facility survived a 7.0 earthquake untouched, which means while the conventional wastewater infrastructure was destroyed, this system survived intact and in the time afterwards continued to purify the wastewater, provide sanitation, and of course provide gas for cooking in the camps, and also some limited product output in terms of zucchini or tomato or other things that they were growing on these sites. So that is a real success story, and it took a long time for the international aid agencies to pick up on it, but by now UNEP has funded a few facilities, and I would say that more or less 50 facilities in various sizes are operating in Haiti, and they're purifying the water of about 100,000 people, providing fuel in terms of cooking gas, providing sanitation in an area where many thousand people have been killed by cholera, and providing a stepping stone for devastated areas to actually build up their own economy again. In summary, what we actually achieve with these projects is a quality of nutrients, profitable nutrient recycling into various crops. We manufacture fertile soils, a very important issue worldwide. We have a quality of energy by using current solar income. We're gaining energy from current biomass. We're using the sunlight as an important purification factor in the water treatment. And of course, we're producing methane with the biogas digesters, which also is an energy source. And we're contributing to social fairness and quality of life, conceptual diversity, innovation, social justice, and some of these sites also have been used for reforestation projects where we grow tree seedlings on the site that are then actually replanted in deforested areas. And that is Cradle to Cradle. Thank you very much.